All right, good morning, students. This lesson is all about analyzing the layers of Earth's interior. And what you're going to want to do is right away is take out page 10 of your reference table, and you're going to want to look at that throughout the lesson because it's going to be a key focal point of the lesson. Today is a little bit of knowledge as well as some skills around how to use page 10 effectively. It's very straightforward. Let's jump right into it. First off, why does the Earth have layers? Well, actually, as it turns out, one thing that we've learned from studying the solar system, from going to the moon and using different technology to study the moon's layers, we find out is that objects in the solar system, solid objects, they all have layers. Even the sun has layers. And for solid objects, the biggest reason why they have layers is because they all started off at one point in their past as a ball of liquid. And as a ball of liquid, the material inside that liquid is free to move within the liquid. So the denser things are free to move towards the core because, again, denser things move down. Lighter things, on the other hand, they rise to the surface. So that's called planetary differentiation. You can think of it as like the planet is becoming different, right? Differentiation, difference. So it goes from being this kind of homogeneous, it's kind of the same everywhere, and over very long periods of time, the Earth, differentiates itself into layers, with the lightest things, the least dense things at the top, essentially floating at the top, and the core being the most dense. All right, and this is page 10. We can see a lot of things going on here, so I'm going to take a minute to go through all the things you can see here, and again, I'll kind of cover it again later. So what we have here is a cross-section of the Earth. We kind of slice through the Earth, and I don't have it here, but you can see the depth along the x-axis on the bottom of your chart. So we're going very, very deep. It's about 6,300 kilometers down, so the Earth is extremely, extremely deep. That's the first thing. We have inner core, outer core, stiffer mantle, the asthenosphere. And then you have to look really, really carefully because there are a lot of layers in here that you can't see very easily. There's the white layer here called the rigid mantle. Then you have the black layer called the crust. And both of those together make up something called the lithosphere. Right? Lithos meaning rock, sphere, so the rock sphere. Okay. We also have these arrows in here, which are convection currents, right? Currents of heat moving inside the Earth. We'll get to that later. Okay, we have different surface features on the Earth. So this is the Mid-Atlantic Ridge. Okay, a lot of this crust here represents the ocean, and then we also have the continents. So this here would represent North America. We have the Atlantic Ocean, but again, it's not water and land. It's actually all land. If you drain all the water, right, it's all a bunch of land. It's all a bunch of crust. We have the Cascade Mountains. We have a trench over here, the Pacific Ocean. We'll go over that later. Along the right side, we have density. And as we talked about, the rocks get more dense as you go down because that's how the planet differentiated itself. We also have two different types of crust. We have the continental crust and the oceanic crust. There's no difference in terms of color here shown. So this entire black line here represents both types of crust. There's really no way to show that at this scale because the ocean crust and the continental crust at this scale would be very, very tiny to differentiate by color. So they just show it as one black line. Okay. So again, two types of crust. The continental crust is what continents are made up of. So think of all the continents. All right. It's less dense, 2.7, than the oceanic crust, which is 3.0. So continental crust is actually floating on top of oceanic crust. Continental crust is typically made of granite, and it's thicker. It's actually about 4 or 5 times thicker than the oceanic crust, which tends to be thin. The thickest sections of continental crust can be like 70 kilometers. Places like Mount Everest is very, very thick, right? Because the Earth is all bunched up from the mountain building. So very, very thick there. But average continental crust is about 40 kilometers thick. Oceanic crust average thickness is about 10 kilometers, I want to say, about 10 kilometers. So it's thinner. That's something you actually have to know, and it has to be just memorized. So continental crust is less dense, that you can see from the numbers, but you have to know from memory that it's thicker than the oceanic crust, which is thinner. Okay. Now we come to the Moho. The Moho was discovered by a, what was his nationality? Oh, a Polish, I want to say a Polish seismologist. He studies, seismologists study the inside of the Earth. In many cases, it could be the deep Earth, it could be the crust. So he was studying the inside of the Earth, and he discovered a boundary that existed between the crust and the rigid upper mantle. Actually, he discovered the difference between those two things. At one point, it was kind of all the same thing, and he realized, wait a second, there's actually a difference in how those two materials behave. So he termed it, of course, the Mohorovich discontinuity. We just call it the Moho for short. It's a boundary between the crust and the rigid upper mantle. And you can see it right here. It's the line that separates the black from the white. All right, it's called the Moho. And there's Mr. Mohorovich. All right. All the layers from shallow to deep: crust, mantle, outer core, inner core. That's like the most basic layers of the Earth. And we should also know their state of matter. So solid, outer core is liquid. We'll get into understanding why we know it's liquid. It's actually a really cool thing how we know that, because we can't go down there at all. So how do we know that? Well, more on that later. So crust, mantle, outer core, inner core, solid, liquid, solid. Now, as you might expect, the temperature, the pressure, and the rock density all increase as you go deeper. So as you go deeper, it gets hotter. As you go deeper, there's more pressure. And as you go deeper, the rocks just get more dense. This is the full page. And the first thing we have to appreciate about this page is that all of these layers here, they all line up. So this outer core layer, it lines up with this chart. The outer core lines up with this chart. And it also lines up down here with the depth. So everything aligns vertically. It's kind of one big chart to understand. All right, so let's just go through each one. Each of the dotted lines is showing the boundary between layers. So I've broken it up here. This first line here is the boundary between the outer core and inner core. This boundary here is outer core mantle, right, etc. This little zone here is called the asthenosphere. We'll get into that. We'll get into that later. What that layer is. It's actually quite interesting. All right. And if we're going to read this chart, I'll just throw a question at you. What is the interior temperature of the Earth at a depth of 1,500 kilometers? Well, you have to go ahead and find 1,500. Well, you can see here each of these vertical lines has an interval of 1,000, so 1,500 is right in between. We move up, we hit the line, and we move to the left. So there it is. We have to read it, and you read it, and it's about, 3,800. You can estimate 3,800 degrees Celsius. So that's insanely hot, right? 3,800 degrees Celsius is very, very, very hot. Another question, what is the interior temperature at the outer core, inner core boundary? We find that boundary. Here it is. We move up, and we move to the left, right? It's insanely hot down there. It's above 6,000. Like maybe we can estimate it's 6,300 or so, right, degrees Celsius. Okay. So just like that. Go up, hit the black line, and move to the left. The exact same procedure is used for the pressure diagram. So this is showing pressure inside the Earth. And these 1, 2, 3, 4, it's not 1, 2, 3, 4, it's 1 million atmospheres. So let's just appreciate that for a minute. Well, 1 atmosphere is right now. So you're breathing, you're living your life, and you are generally under 1 atmosphere of pressure. It's very comfortable. This is 1 million atmospheres. So that is much, much greater. Much, much, much greater. And you read it the exact same way. So what is the interior pressure at 2,000? Well, you start at 2,000, you come up to the line, you go to the left, and you have to estimate. It's about 0.8 million atmospheres. Remember, it's million atmospheres, not just 0.8. million atmospheres. All right, same thing. Outer core mantle boundary. I'm just giving out random questions here. There it is. There's the boundary. We come up to the line, come to the left. We estimate, it's about 1.5 million atmospheres. All right, and the very last thing is pressure, depth and density. So the rocks get very, very, very dense as you get towards the center. And actually the center of the Earth is iron and nickel. There's also a bunch of other things. But actually using our understanding of meteorites actually give us an idea of what the inner core of the Earth probably looks like. Meteorites are leftover material from planet formation, so those actually give us an idea of what the inner core of the Earth probably is. That's how we know. One way we know that it's iron and nickel probably down there. All right, last thing, just to give you some context about how insanely huge the Earth is and how human efforts to this point have come nowhere near penetrating the Earth very deep at all. The deepest cave is about a mile down, which is obviously insanely deep. The deepest wells, this is the Kola well. You can actually read up about this. 7.6 miles deep, which is, let's be clear, very, 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 very deep in the Earth. But that is not even close to scratching the surface of the Earth itself. So the crust is, you can see it's showing here 22 miles, okay? At least that's the estimate it's showing here. We're not even halfway through the crust itself. And if we just go back, just so we have an understanding of how little that is, okay, if this was to scale, if this whole thing is to scale, I don't think it is, we'd be halfway through that black line there, right? So humans have come nowhere near understanding, at least with physical evidence, what the deep inside of the Earth actually looks like. We have to use our understanding, or we have to build our understanding of the Earth using other methods. And those methods include using earthquakes and using waves. Going back to this, I'm going to flip back here really quick. This seismologist here, that's how he figured this out. He has to use remote sensing. He has to use earthquake waves to understand the inside of the Earth and do a bunch of math. It's a lot of math to figure these things out. Okay, that's today's lesson. You'll have a test wizard on this, and I will see you all tomorrow.